Started. Good morning, everyone. For those in the US, and good afternoon to everyone in the UK. Welcome to this week's Heart BDTK Technical Conference. Today we'll have one presentation, and we are scheduled to end at the latest 9 a.m. Pacific time. The presentation will be recorded and accessible online once we've processed it. And if you have any questions during the presentation, please type it in the message box. Also, please mute your mic to prevent any background noises. Carlo Zaniolo from UCLA will be presenting about supporting end-user questions, queries, and searches on knowledge bases. Without further ado, allow me to introduce Carlo.
Okay, I'm going. That's the first time for me.
Yep.
So bear with me. I'm not very familiar with the system, but let's try the best, right? Okay, so what I'm going to talk about today is something that you're very familiar with, which is, basically Wikipedia. But I will try to put that in a new light, because in fact, Wikipedia is having a tremendous impact on, the way that we do research and the way we do the research. Can you hear me? Yes. But basically, I claim that it can have, Wikipedia is the center of a number of knowledge-oriented initiatives, right? And of course, but the important thing is that it can have a transformative impact on science and modern society. And of course, a natural parallel there is the famous Encyclopedia of Diderot and D'Alembert, who really transform, as a landmark of the age of the Enlightenment. So the idea, I think, is that Wikipedia may have a tremendous effect also on information age. And from the technical viewpoint, I see basically the strength of Wikipedia consisting in the fact that it combines various aspects of information, including the text, hypertext, but also structured information, such that you find in knowledge base or databases, okay? And, in fact, the knowledge base are derived from what's known as the info box in Wikipedia, and can support, simple questions, but complex queries, and also high precision document retrieval. Just to give an example, to give you for example, let's take a San Diego page. Let me tell you, what I'm talking about. So you see in the page, you see text, hypertext, with links, of course, but also you find the info box, okay? And if you see for a second, you immediately realize this info box is a structured information, right? Having to do with country, state, total population, okay, here at the bottom, okay, of the page. And all that has been manually actually transformed into a structured knowledge base that I show you here, which is known as DBpedia, right? Where of course you see, basically the same information. Although, for instance, there is a standard, coding for all representation for every piece of information, which is unified across the Wikipedia, right? Whereas, for instance, at the level of the individual web and at the individual web page, you could find, the user may write something which is more suggestive to their taste, but if we write a population here, they wouldn't. Whereas, of course, the internal representation and population total ranking. Okay, and the point, of course, is that it's very hard for a casual user to bridge this gap and to know that, in fact, internally, population is really DB population total ranking, okay? That's one first problem. So the internal representation of the data in DBpedia is the first problem. And the second problem, of course, is the fact that, they have to learn a query language such as SparkQL in order to access this knowledge, okay? So Wikipedia semi-curated multilingual web document corpus, which is widely used and, very popular, okay? DBpedia organized using ontologies the information taken from the info boxes into a knowledge base. And those are RDF triples, right? They support structured query languages such as SparkQL, okay? The problem, of course, is end user right now cannot access the riches of DBpedia without having to learn SparkQL and install the internal knowledge bases, which, by the way, those are also a burden for even for the programmer, okay? All those unique names, you have to find what they are, okay? And there are thousands of. So, the usability of this framework is not great, okay? On top of that, you have the problem that there is a lot of incompleteness and inconsistencies, largely because, DBpedia has been created by a large number of volunteers, right, which do a very good job, but, over time, over different languages, because, of course, we support different languages, inconsistencies and incompleteness are bound to occur, okay? So we have today, actually, we focus on the first problem, okay? The end user access to make the Wikipedia more usable, okay? And we'll talk about other problems later on, all right? So basically, to make things more usable, we explore two approaches, okay? The first is the Swype approach, which basically works with the very info boxes which generate that information, which provide that information, and turns them into active forms, okay? Where user can enter by example structured query, okay? So, of course, the user must have a browser for that, right? The second, yes? The second approach, okay? Okay, fine. Okay. The second approach is the Canali, where we use a natural language interface, which of course is a special kind of natural language interface, in the sense it's a controlled natural language interface, and we'll tell you more about, okay? But which also is supported by an auto-completion query system, which assists the user and eliminates some of the ambiguity, okay? We will describe that later, okay? And and we have other things which we are doing, and we'll tell you more about. Okay, let's move on to the next slide. Okay, let's talk about Swype. Okay, first of all, you have to start with the page of an entity like the one of interest. Okay, then what you do, you have to enter a query by example. You're familiar with that, query by example condition into the active form, into this, info box which has been activated, okay? And then you have to launch the query, okay? For instance, take an example. Suppose you want to find all universities that have more than 2,000 faculty members and were established before 1900, okay? What you can do is to go to any page of any university, and since we are at UCLA, let's go to UCLA, right? Immediately you will concentrate on the info box, which is shown here, right? Which you find, for instance, various things, including established, etc., right? Okay, so what you have to do then, you have to enter the QB condition to the activate info box, okay? Which you can do, of course, by, let's enlarge the info box just to show you what could be there. And immediately you see that it was established in UCLA in 1882. In fact, there are two numbers, okay? And that's, a little bit of ambiguity, but as you put your pointer, okay, or on this field, immediately what happened is that the system helps you, okay? And it gives you, there's only one active field, which is this one, the first one. The second one is a comment introduced by the user, okay? But it's not part of the DBpedia database, okay, the knowledge base. So what you will want here in the red field activated, you just enter a condition, which is, before 1900, and then down here, you ignore, of course, the footnotes, and you just enter academic staff 2000 or more, right? And then, of course, the last thing that you need to do is to launch this whole query, and you get back, the results, which in the typical form that Wikipedia returns to you if you're going to ask a keyword-based search, right? Also, it is a summary of what you have asked, okay? And if you really want, you can even see the SparkQL current query, which tells you, what in fact you're getting there, but also tells you all the internal names of, used by DBpedia. So this kind of box is also useful to actual programmers, okay? Not only to end users, right? But so this is a very powerful framework, okay, which is available and has been demonstrated several times, okay? But of course, there are so, okay, you can ask complex queries such as, find all the famous musicians who were born in Vienna and died in Berlin, okay? Well, immediately you realize that, there is some kind of joins, which is needed for that. And, sometimes you want to ask, aggregates, okay, to count musician, or perhaps to group each musician, who were born in Vienna by the place and the year when they died, okay? So there's all that rich structure that you can use for analysis and, further investigation of the information. Also, an important thing is that, structured query can also be combined with standard keyword search, In other words, the slot which Wikipedia now provides to enter keyword query is still available on the Swype. And the queries that you enter in the form and in the keyword box are then combined, okay? And what you get back is the results that satisfy both, okay? And this is very important because right now, most of the keyword queries have a very poor precision. Of course, they get good recall, but they get good recall by returning thousand, millions, in the case of Google documents, which are only vaguely connected to your query, okay? For instance, we were trying to investigate, as you know, law schools are facing a crisis because low employment. Also, students are facing a crisis because the bar pass rate has become, much more difficult to pass a bar. So now the bar pass rate is below the traditional average. So what we wonder is whether this was true everywhere, okay? So why don't we go ask the query and say, give me the bar pass rate for Ivy League schools, law schools, okay? Well, of course, Wikipedia returned about 2,000 results, okay, when we used this using only keywords. And there were, the obvious one at the beginning, but so there were less obvious ones, like, for instance, Batman and the Poison Ivy, right? What is Batman, the Poison Ivy? Because in fact, that was according to keywords, the word Ivy was connecting enough that that page was returned. Okay. Now you must absolutely understand the following: that whenever you have, you go to Google or to another search engine to buy a refrigerator or to buy an appliance, the most popular ones are the most interesting ones. However, if you are a scientist looking for something which is not in textbook, but in some paper which has been published, you probably end up searching the tail end of the query answer, okay? And, the fact that you can get, in fact, fewer query answer, a more precise query answer is extremely important, to help a scientist, okay? In fact, that's also something which is being recognized by Google, which, realized that the tail end of the search result is often the one which is the most important, okay? Okay. And that's why this combination of structured queries and keyword search is very important because, in fact, at the end, by using instead Swype, we ended up getting back only 6 schools, okay? 6 schools, okay? That's very important, okay? With their bar pass rate, all right? So that's demonstrate, that really that's the way, the kind of, query capability that, most in-depth researcher would like to have, rather than, the wide specified, answer that you now get from the search engines, right? Of course, you can also make another point, that this query engine, or this capability probably it would be wasted if you have a very simple question, such as how tall is Claudia Schiffer? Of course, if you wonder to have how tall Claudia Schiffer, right? There's no point in going to the, search for on a web page for an actress. Okay, you can, and then ask, use Swype to ask that question. You can very well look for the Claudia Schiffer page and find right there what is their height. Okay, so the problem, of course, is that you're still limited by the fact that you use the browser. Okay, natural language. On the other hand, we have developed another system where the user will in fact employ natural language, and so there is no need for browser. Okay. So let me take you now to the next story, which is the natural language system. Okay, and basically, when it comes to natural languages, there's been a long history of trial and error. Many systems have been built, and basically they fall into big groups. Okay, the first group is the unrestricted natural language system. Okay, which basically relies on a very smart parser, okay, for a particular language, and the parser breaks up the text into chunks, and then each chunk, okay, each phrase is assigned, an interpretation with a high probability, okay, the most probable interpretation, okay. However, when you come, particularly for long sentences, even small errors in each single assignment often produces a high probability error, okay, on the whole sentence, okay. And then, so, the precision of the system is never guaranteed, okay. Particularly because certain natural language questions are intrinsically ambiguous. For instance, who are the spouses of American football players born in Los Angeles? Here, of course, the question is, who are you asking, whether the spouse is born in Los Angeles or the football player is born in Los Angeles, okay? Canal is able to avoid this problem by basically having an enhanced natural language system, which, I will tell you more about, okay? It has some additional benefits, okay? So Canal, however, is the second type of natural language system, which is also very popular, which is called a controlled natural language system. So a control, which is basically means that you restrict the natural language to reduce ambiguity and to achieve real-time translation. So that's very important, real-time translation. But of course, excuse me, this is a very difficult compromise that you have to, trade-off that you have to decide on, because with too much control, the language is no longer natural. With too little control, there is much ambiguity which remains. So, well, apparently, Canali found the right compromise, because, in fact, our system was able to win. And first of all, it was able to be accepted for the competition, which meant it was natural enough, okay? But then also won the competition, the Quiet 2000 petition, which is query answering over linked data, okay? This is a competition which is run every year, okay? And also, our system not only did that, but also it was fast enough to, there's another important advantage that Canali has, right? Is able to support real-time answer completion to resolve, to help user resolving ambiguity. Okay, by using controlled natural language, the answer came, the system is able to operate with enough speed to support, the real-time answer completion. Okay, and also it has some other capability, which I will tell you, which we are trying to extend, into supporting hybrid structured query plus free text search. Okay? Let me tell you a little bit more. Okay. So the Canali, let me tell you what the system works. The Canali system accepts sequences of basic phrases. Each basic phrase denotes an element of the RDF graph. Okay, spiced with syntactic sugar. Okay. The acceptable phrase has a finite. Basic idea of Canali is the ability to operate a finite state automaton with online user guidance. Okay, providing the the user with online guidance. Okay, because there's this real-time auto-completion for user to enter the question. Okay, so the idea is that the user will not be able to see an auto-completion unless their question or that part of the question they have entered so far is interpreted unambiguously by the system. So there's never an issue of wrong questions. For instance, take the following query. What is the capital of countries having population total greater than 100 million, right? Well, what does Canali do? Canali start with the initial state, okay, which is, and then you go to what is, right? Okay, what is, it takes that to state S1 because, you are looking for some sort of entity. And then you get the capital, right? The capital is a property of the query of the RDF representation. Okay, remember RDF representation have entity, attributes, and properties. Okay, so capital, okay, would be a property of this entity. All right. Which, of course, bring you back here, so because we are still in the property of an entity. Then the next thing, of course, of countries. Oh, now you must specify the entity. So you said, countries, which will be either an entity class or an entity instance. Okay, clearly, country is an entity class. And then there's another thing, having, which is more property I'm going to specify. And the next property will specify population. Okay, so having more, you still, in S3, still an entity population total, which of course goes back and say another attributes. Okay, and then you get, all right. And now there is a specification which says greater than, of course, which is the operator. Okay. And then you give the, the literal, which is 100 millions, right? Which takes you back here, and finally the question mark say, okay, that's my question, give me the answer, okay? And that's what you get as a result. You get, the answer. But before you get the answer, all along, while you're getting this answer, you see the system which tells you how far of that query the system is being able to interpret. Okay, so because when you say where is the capital of, having population total. Okay, when you see this is the part which has been interpreted. Okay, account has been interpreted, but this part has not been fully understood by the system because there are three possibilities: population total related to the countries, population total related to the capital, and then population ruler, which is another thing which I think you're familiar with in UK, is is kind of suburb, extended cities, right? So immediately, the user at this point, since there's an intrinsic ambiguity in the language, will be able to hit probably related to the countries, right? Because 100 millions, probably there's no city at that size. And the result, of course, is that you get these large cities, right? In the form of snippets, right? Which you can, of course, you can get the name of the city, you can get a link, so you can click for more information, the typical kind of situation that you want to obtain. So you see how natural language, okay, has brought you an answer which integrates both a question, which will be answer, which will be Tokyo, for instance, and Beijing, if you only want the name of the city, but then it will also be you know, the standard information retrieval, because that you can obtain by clicking on this link. So the question is, how effective is the system? Well, there's been, you know, the Quark initiative, which of course is an abbreviation what which I've described before, has developed a series of test beds for evaluating the effectiveness of various Q systems. Okay, there's this competition, and the results are evaluated in terms of the precision recall, where, you know, you take, you know, for basically the idea is that perfect precision, perfect recall, 100%, you will get the answer of 1, okay? So we get an answer of 98% with our system. Well, that's what we claim. In fact, that was not what the tester in Heraklion, Greece, claimed. They claim we only got an F index of 89. Okay, on the answer we answer, and there is another index. Okay, and in fact we are going to dispute that result until we were told that in fact was the best. Okay, and so let's live with that. Right? These are kind of the finalists at that competition. And you see that some of them are very low, okay? And some are very good too. Yeah, this is an area where it needs improvement, but there is already some substantial good results, okay? And this is, you know, it's relatively compact and it works fast and allow, in fact, this fact that you can return the answer completion in real time to assist the user. If you go with a full natural language situation, you know, this capability of a real-time interaction may be lost. We also had a couple other applications of Canali. They use, you know, used to be using brains. Actually, there's a bug here. Should be a Z here. The Open Music Encyclopedia, and the other one is an ontology we have derived from 3 systems. One being CIDR, the other disease sum, and the third drug bank, and which answer query relating to drug side effects. Right. So there's been. So there have been tests of other systems, right? So basically, overall, the situation is quite encouraging, right? There's been substantial progress in user interfaces on top of these knowledge bases, okay? And what we're addressing now, we want to address next, is the hybrid questions in natural languages. Hybrid question being those questions which combine, you know, structure query with keyword search, which we think are extremely important for scientific searches, right? Swype already has that capability. In Canali, we're trying to introduce, okay? Another important direction which will make some, you know, significant progress is the historical information, okay? For instance, you know, now we have DBpedia, we have all the information about the current situation with cities. Of course, we would like to also store information about the history of the city, so you can ask questions such as who was the mayor of San Diego on January 1st, 2009, okay? And then, of course, there is the problem of aggregates. Sometimes you want to collect very complex queries which aggregate results, okay? That's a big open problem. And in fact, there is another competition, okay, which works on giving people access to RDF data cubes, right? And we also participate in that competition, but we only got, I mean, I'm not going to tell you more about because we only got the second prize on that one. Okay. So what is the conclusion which you can draw from this? First of all, the Wikipedia, DBpedia, the model and the tools for Wikipedia can be very active for curating semi-curated copies of scientific and medical documents. They become very accessible via user-friendly question and answer. Okay, that's our contribution, to make them accessible through user-friendly question and answer. Okay, and as I said, there are questions, there are queries, which means a question with more structure, and there are simply searches for pages. They all become fused and integrated in the same framework. Okay, but the important thing is that this framework offers a precision and recall which are superior to that much superior what other search engines can offer now, and in fact I think can be really used in the scientific searches to support scientific research. Okay. But of course, some problems like inconsistency and incompleteness of knowledge bases are still much needed, and we work on that. There is a system called IBminer, which in fact we have developed. We are trying to test on patient case reports with the help of Dr. Liem, and we are also trying to apply to PI reports, okay, and see what more results we can get on that. So let me finish by acknowledging those who have contributed to this research, and also to take this opportunity to thank you and, of course, our research project. And now, with that, I have some more references, and I'm open for questions. Thank you.
This is Andrew here. Maybe I'll start. So, both systems that you mentioned work off of DBpedia data currently, and how does Wiki Data factor into your thinking for the future?
Oh, that's a very good question. Okay, very good questions. In fact, how to get better information. At this point, I think it is very relevant, but we haven't decided yet how it would be included, in our system. Clearly, the best idea, the ideal situation would be that DBpedia, make better use of Wiki Data. Okay, but I'm not sure that's the case because it seems to be two independent organizations. Okay. We also talk about starting our own version of the DBpedia, but our resources are limited. Okay, so yeah. So basically, the bottom line is that that's something to be considered, and also, of course, there are other things like the multilingual aspect of DBpedia. But so far, we don't have any specific plan to really use this additional information, which can be very useful though.
I'll just chime in that, we've been pretty reasonably active in terms of loading biomedical data into Wiki Data, and I think being within that community has, you see a lot of the warts, of course, but there are also a lot of advantages. DBpedia, of course, is the accuracy of the extraction from the Wikipedia info boxes is highly dependent on the quality of the extractors, and it's not always perfect. So a lot of the stuff we were doing as far as genes and proteins within Wikipedia were not being correctly extracted into DBpedia, and so Wikidata just sort of takes the middleman out of it for us. Right now we just directly deposit into Wikidata, and there's using the programmatic interfaces, using their pseudo ontology predicates. Anyway, so I would just say that's been a positive experience for us.
Well, that's very interesting, very important, and I'd like to talk with you more about, because we may in fact do something like that. Clearly, the situation, as you say, Wikidata is certainly a step forward, okay? However, then you also need better tools because the crowdsourcing in process is quite, laborious, okay? And if you don't have immense resources, or if you are concerned, for instance, about the privacy of the data, you need to automate it. You need to have very few people who work on that, and they can use automated tools as much as possible, basically to carry out the big task. And that's the area in which we are trying to move to, having this IB miner, which is in fact able to automatically extract information from the text. Okay, and certainly that's one thing which we could see in the future, right? I know that you can also have other approaches, in fact, such as tagging the text, and that will help too. Okay. But probably, there is a real need for having a system which understands most of the text, okay? At least is able to identify particular phrases or significance, extract them from the text, and populate a knowledge base with that, right? Because, as you said, textual databases will remain with us for a long time, particularly in the medical profession, right?
Yes, makes a lot of sense.
Thank you. So I was looking forward to hear more about your recent work. Okay.
Absolutely. Can I ask one other question? You alluded very briefly to this question answering based off of CIDR and Diseasome and Drug Bank. Can you expand a little bit on that? The types of queries that you're planning to answer?
Most of this was done by a summer student, okay, because it's sort of interesting. And had no medical background. It was basically integrated these three knowledge bases. And the queries were demonstrated, the question was demonstrated most, was the side effects of drugs. Okay, that was the main kind of queries, that were demonstrated. And so I don't know, we still need some work there, but basically the concept that you could take existing ontologies, put them together, and then have this Canal System work, use those ontologies was demonstrated, okay? Of course, as I told you, there is a controlled natural language, so one of the things that you want perhaps to define always the language itself to make it look a little less artificial, okay? So there is some work to be done there. And there, basically what we did, we took some of the basic queries because, we didn't really have that much enough knowledge about, the kind of typical queries that medical users, so, even patients would want to have to ask. But there's certainly one area which can work. In fact, the students coming back this summer, so that's one thing that we could do and follow up on that. Okay, that's it.
Got it. Thank you.
Thank you. All right.
Are there any other questions? Okay, if not, thank you, Carlo, for the great presentation. So that concludes today's conference. And that also concludes the technical calls for the summer. We'll start up again in the fall, so be on the lookout for an email in September. But yeah, thank you everyone for attending.